Hey guys, welcome to another lecture video for Chem 115. In this video, you will learn about polyprotic acids and polyprotic bases. Also, you will learn how to calculate the equilibrium concentration of each substance that's present in the chemical equation. You will also learn how to write the chemical equations for each ionization step for weak polyprotic acids and weak polyprotic bases. Lastly, you will learn how to calculate the pH of a solution that contains a polyprotic acid or a polyprotic base. Feel free to pause this video at any time to ensure that your notes are complete. So let's get started. To introduce this topic, the first question that we are going to ask ourselves is, what are polyprotic acids and what are polyprotic bases? Simply put, polyprotic acids are substances that contain more than one ionizable hydrogens. And polyprotic bases are substances that can accept two or more hydrogen ions. Now, you guys have come across polyprotic acids and polyprotic bases at some point in your first semester of general chemistry. One example of a polyprotic acid is carbonic acid. Another example of a polyprotic acid is sulfuric acid. For a polyprotic base, one example is going to be carbonate. Another example is phosphate. And so we're going to go ahead and look at the differences, the key differences between polyprotic acids and bases to that of their monoprotic form. And so when we're looking at, when we're comparing and contrasting the monoprotic and the polyprotic form of these acids and bases, what we're looking for is the number of ionizable hydrogens for acids. Now for bases, we are looking for its ability to potentially accept two or more hydrogen ions. So looking on the left-hand side, for monoprotic acids, this is just a short list of monoprotic acids. So these are not all of the monoprotic acids that you guys can come across in the world. And so if you are looking at hydrochloric acid, nitric acid, hydrofluoric acid, and hypochlorous acid, all four of these examples only has one hydrogen. And so therefore, it can only ionize one time. And so what I mean by ionization is, for example, we have HCl. And when you place HCl in solution, this hydrogen ion is going to separate from the chloride ion. And since this chloride ion has no more hydrogens, this compound HCl can only ionize one time. Now, if you guys are comparing that to the polyprotic acid, you'll see that for polyprotic acids, there are two or more hydrogens that's present in the chemical formula. And so what that means is that these types of compounds can ionize twice, and it usually happens in two steps. And you guys will learn how to write those steps in just a second. Now for monoprotic bases, notice that for hydroxide and fluoride, the charge is -1. And if we're looking at polyprotic bases, the charges are like -2 or -3. And so what this basically is showing us is that a monoprotic base, since it has a -1 charge, can only ionize a hydrogen from a water molecule one time. So what do I mean by this? We're going to go ahead and take a look at fluoride. And so fluoride is a weak base. And now, even though it's a weak base, it has an extra lone pair to donate to a hydrogen from a water molecule. And so if you watched my previous videos before, you'll kind of see this mechanism occur. So here you have a Lewis base, which is the fluoride. So I'm just going to go ahead and put in Lewis base. And then it's going to go ahead and donate that hydrogen, or donate that lone pair to hydrogen. And this arrow forms like a covalent bond between fluoride and this hydrogen. And then the electrons that's present in this covalent bond is going to go back to oxygen. And so what you get is the conjugate acid, HF, and hydroxide. And so this is the conjugate acid of F minus. Notice that once fluoride picks up a hydrogen, the charge disappears. And so since there are no more extra lone pairs to donate, HF cannot ionize another hydrogen from a water molecule, from another water molecule. Now, if you guys are looking at a polyprotic base, for example, S-2, notice that it has a -2 charge. And so if it ionizes one hydrogen from a water molecule, the result that we're going to get is going to be HS with a -1 charge, right? And so since there's only one hydrogen that's picking up, we're going to go ahead and change the charge from -2 to -1. So this is telling us, and then we're going to have that hydroxide. And so this -1 kind of informs us that it has another lone pair to kind of donate. And so therefore HS with a negative charge can, swim around the solution, find another water solvent, and then donate that extra electron to a hydrogen from this water molecule, ionizing it to form H2S, or hydrosulfuric acid, and we get another hydroxide. And so since there are 2 ionization steps, that is characteristic of a polyprotic base. Okay, so hopefully you guys kind of understand the key differences between monoprotic acids and monoprotic bases to that of polyprotic acids and polyprotic bases. So the next thing that we are going to learn is how to write the chemical equation for weak polyprotic acids and weak polyprotic bases. And then we're also going to learn how to associate the correct equilibrium constant to each of these equations. And that's really, really important, especially for this specific topic. And so there's a couple more terms I want to toss around. This word diprotic acid, so di represents 2. Protic represents a hydrogen ion. And so this acidic compound will contain 2 ionizable hydrogen ions. And so the same idea with a diprotic base, this compound, this substance, can ionize twice. Okay. And so what we're going to learn how to do is to write chemical equations for weak polyprotic acids and weak polyprotic bases. Now, since these compounds are weak, in other words, its equilibrium constant is less than 1, we will have to describe the ionization of the hydrogens in two separate chemical equations. Okay. And so we're going to go ahead and take a look at a specific example. So carbonic acid. And so carbonic acid has two hydrogens. Now, since carbonic acid is a weak acid, when you drop this substance in water, forming a solution, both of these hydrogens do not separate at the same time. What happens is that there's a stepwise dissolution or ionization of each of these ionizable hydrogens, and that's what we want to try to capture in our chemical equations. And so what we're going to do is we are going to write the chemical equations for the first ionization step, and then we're going to go ahead and take a look at what that equation looks like for the second ionization step. So since this is an acid, we're going to go ahead and ionize this compound only once. So this is the first ionization step. So that results in one hydrogen being separated from its parent compound, producing hydrogen ion and, oops, that's not the right charge, and bicarbonate. And so this chemical equation represents the first ionization of carbonic acid. Now, if you notice, the second product, bicarbonate, still contains another ionizable hydrogen. And so what we're going to do is we're going to learn how to write the second ionization step. And so we're going to go ahead and take this product, since it still contains a hydrogen, and then we're going to go ahead and write it as our reactant for the second ionization step. And once again, when we're ionizing this, we're just simply separating the we're simply separating the hydrogen ion from its parent compound, producing H plus and CO3 2 minus. Okay. And so if you look at our final product, notice that carbonate no longer has any more hydrogens to ionize, and so we would stop here. Now, if there are 3 ionizable hydrogens, then there are 3 ionization steps. And we'll look at that in just a second. Now, let's go ahead and go back and look at this first ionization step. And so when we have carbonic acid and it ionizes one time, the equilibrium constant that's associated to it is Ka1. Let me move this arrow just a little bit down. Okay. So this 1 represents the first ionization step. And so here, when we have bicarbonate and we're ionizing it a second time, the equilibrium constant is going to be represented as Ka2, or the second ionization step. Okay. All right, and so that's pretty much it for diprotic acids in terms of writing the chemical equations for a weak polyprotic acid. Now we're going to go ahead and do the same thing for a diprotic base. And so if you guys are looking at a diprotic base, so let's go ahead and just look at CO3 2 minus, so carbonate. Very similar to what we did with when we were comparing and contrasting the polyprotic base to the monoprotic base, since carbonate has a -2 charge, that means it has the potential to ionize a hydrogen from a water molecule twice. They're coming from two different water molecules. And so let's go ahead and write the first ionization step. For this substance, carbonate. Now, whenever we are working with a base, you always want to include water in the chemical equation, just because that's a source of the ionization. And what's going to happen is that one of the hydrogens is going to be transferred over to carbonate, very similar to the mechanism that I showed you above. And this produces HCO3 and H plus. I'm sorry, not H plus, OH minus. Okay. And so, since we're adding one hydrogen to carbonate, and remember that hydrogens are positive in charge, that means the charge at the very end, it's going to increase. It's going to get closer to 0. So -2 is going to go up to -1 because we added a positive value to it, or a positive charge. Now, since the product bicarbonate still has an extra lone pair, it can undergo a second ionization step. Okay. And so here we have HCO3, -1. And once again, it's going to take one of the water molecules, or it's going to take one of the hydrogens from another water molecule. Okay. And this will produce H2CO3 and another OH minus. Now, I'm not writing my physical states of matter for these equations, but know that everything is aqueous except for water. And so water is going to be our solvent, so we're going to assume that's liquid in form. All right, and so since the first ionization step is describing the first ionization of the base, we're going to go ahead and represent the forward reaction as Kb1. And for the second ionization step, looking in the forward direction, we're going to go ahead and write Kb2 to describe the equilibrium for the second ionization step. Okay. And so this gives you guys a preview of how to write chemical equations for diprotic bases for each of these ionization steps. Now, another item that I want to mention before we move on to the next topic is the relationship between Ka and Kb for diprotic acids. And so I'm going to go ahead and zoom out just a little bit. Perhaps I'm just going to go ahead and move my work just a little bit lower just so it's not too cluttered. All right. So let's go ahead and compare and contrast the diprotic acids and the diprotic bases. And so if you look at, for example, carbonic acid. And so in the forward direction, carbonic acid is going to be produced by carbonate. And so when we're looking at the diprotic base, the equations on the right-hand side, carbonic acid is found here. And if we're going in reverse, if you will, bicarbonate is found on the left-hand side. And so if you take a look at these two chemical equations, and we're going to go ahead and disregard the H plus and the OH minus for now. And so I'm disregarding this H plus and OH minus just because it's not going to go ahead, it's not going to drive the point home. And so anyways, if you guys are looking at these two equations, notice that the position of the carbonic acid, oops, what happened? The position of the carbonic acid and the bicarbonate is opposite to that of the second ionization step. And so when you guys are creating a correlation between Ka and Kb, for monoprotic acids, it's pretty easy. It's just like Ka times Kb is equal to Kw, and you don't have to think, twice about it. However, for diprotic or polyprotic acids and bases, you have to be very careful with your Ka values and your Kb values. In the forward direction, that's going to be represented as Ka1. Okay. Now, if you guys are looking at the direction in reverse, where we're going from HCO3 back to H2CO3, it's basically represented by this chemical equation. So notice HCO3 is going back to H2CO3. And that equilibrium constant is represented as Kb2. And so once again, for monoprotic acids and monoprotic bases, it's just Ka times Kb equals Kw. However, for polyprotic acids and polyprotic bases, the equilibrium constants, it's very, very specific. Okay, and so now if you guys are looking at, and I'll do this in a separate color, let's just say pink. If you guys are looking at the second ionization step, notice that bicarbonate is found on the left-hand side and carbonate is found on the right-hand side. Whereas if you guys are looking at the first ionization step of the diprotic base, carbonate is on the left-hand side, which is, the opposite position of where it was in the second ionization step of a diprotic acid. And last but not least, the bicarbonate, the HCO3 negative, is found on the right-hand side of the arrow in the first ionization step of the diprotic base, which once again is going to be opposite of where it's found in the second ionization step. So notice here, HCO3 is on the left-hand side of the second ionization step of a diprotic acid, whereas the HCO3 is found on the right-hand side of the arrow for the first ionization step of the diprotic base. And so what that's telling you is that these two chemical equations are opposites of each other, such that their Kb1, such that Kb1 is related to Kb2. And so when you guys are writing the relationship between Ka and Kb for the second ionization step of the acid, it's going to be Ka2 is going to be related to Kb1. And that's going to equal to Kw. Okay. So this is something that you guys definitely need to pay attention to when you guys are applying this in a word problem type of setting. And we'll take a look at that in just a few. All right. And so let's go ahead and go through the motions for triprotic acids and triprotic bases, just so you can see how those chemical equations are written, as well as the relationship between Ka and Kb. And so we're going to go ahead and write the first ionization step for this triprotic acid. And we're going to go ahead and use phosphoric acid as our example. And so the first ionization is going to be represented by the equilibrium constant Ka1. And when the first ionization occurs, you guys are going to get H2, PO4, and then a hydrogen ion. Now, if you guys recall, a phosphate is originally -3, and a hydrogen is a +1 in charge. And since there's 3 of them, we have a +3. So if you're separating one hydrogen ion from a phosphate, the overall charge here is going to be +2, just because you have 2 +1 charges. Oops. Let me erase some of this. And so the charge on phosphate is still going to be -3. However, since you have an overall charge on the cation side as a +2, then if you take the sum of these two values, you get -1. And so that lets you know that the overall charge for this compound is going to be -1. Okay, so that's another way to determine the charge of your conjugate after you've separated one hydrogen from it. Okay, and so here notice that there's 2 more hydrogens, so that's 2 more ionization steps. And so we're going to go ahead and write the second ionization step. So we're going to take H2, PO4, -1. And since this is the second ionization step, we're going to represent that as Ka2, or it's going to be represented as Ka2. And that leaves us with HPO4, -2 in charge, plus another hydrogen. And once again, if you notice, the result of this compound still has 1 more hydrogen, so we need to write a third ionization step. And so here we have HPO4, 2 negative. And since this is the third ionization step, we're going to represent that as Ka3. And what we get is phosphate and another hydrogen ion. And so all 3 of these chemical equations demonstrate the stepwise ionization of the weak acid, phosphoric acid. Okay. All right, and so we're going to go ahead and do the same we're going to apply the same logic for triprotic bases, and we're still going to use the same anion. So since we have phosphate as our anion, we're going to go ahead, that's what we're going to go ahead and start with. And so we're going to go ahead and write the first ionization step for phosphate. And so here we have PO4, 3 negative, plus, now since this is a base, we are required to write water, because that's where the ionization comes from. And so since this is the first ionization step, and we're talking about a base, this is going to be represented as Kb1. And so the result of the result of this ionization is going to produce HPO4, 2 negative, plus an OH minus. And now we're going to go ahead and take the product, this product, And we're going to go ahead and write the second ionization. Okay. So if you notice, there the charge is -2, so we still have extra electrons to donate. Now another water molecule is going to come in, and once again a hydrogen is going to be transferred. So this is through the mechanism of a Lewis base, if you will. So a lone pair is going to be donated to that hydrogen, thereby extracting it out of water. And the result is going to be H2PO4, this time with a -1 charge. Let me write that just a little bit more clearly, plus another hydroxide. And since this is the second ionization, we're going to say Kb2. Next, we're going to go ahead and take the product, and we're going to write the chemical equation for the third ionization step. So here we have H2PO4, the -1 charge. And since we're talking about a base, the ionization occurs when a hydrogen from a water molecule is separated, and then it goes to the base. So that's going to be Kb3. And the result of that is going to be H3PO4 plus another hydroxide. All right. And so these equations, these 6 equations that I wrote down for the triprotic and triprotic acid and triprotic base represents the stepwise ionization of them. And so what we're going to do is we're going to look at the relationships between the Ka values and the Kb values. And so I'm going to go ahead and use pink this time. That's my first color. And so here in this case, phosphoric acid, it's found on the left-hand side of Ka1. And if you look at your triprotic bases, notice that your phosphoric acid is found at the very bottom. And just to make certain that we're looking at the right conjugate, the correct acid-base conjugate pair, we're going to go ahead and take a look at the product. So H2PO4 is found on the product side of the first ionization for the acid, and it's found on the reactant side for the third ionization of the base. And so it looks like the first ionization of that acid and the last ionization of the base are related to each other, right? So the conjugates are just, opposite of each other. And so therefore, their Ka values and Kb values are also related, such that Ka1 times Kb3 is equal to Kw. Okay, so that's something that you guys have to keep in mind. All right, and so I'm going to go ahead and use orange this time. I'm going to look at my second ionization for my triprotic acid, and I see H2PO4 and its conjugate HPO4 represented as Ka2. And so if I'm trying to look for both those conjugates in my triprotic base, notice that H2PO4 is found on the product side of the second ionization of my triprotic base, whereas the HPO4 is found on the reactant side of my triprotic base. And so in this scenario, the second ionization of the triprotic acid and the second ionization of the triprotic base, they're both related to each other. And we can go ahead and conclude that Ka2 is related to Kb2. So we're going to go ahead and write that down. So Ka2 times Kb2 is equal to Kw. And so I'm going to go ahead and use another color. Let's go ahead and do green. If you look at the third ionization step for this triprotic acid, it's HPO4 2 negative, and its conjugate is going to be phosphate. And so we see phosphate in the first ionization step of a triprotic acid, and we see its conjugate HPO4 on the product side on the first ionization of a triprotic base. And so since these two are since these two conjugates are related to each other, these chemical equations are also related. So therefore, or I'm sorry, these chemical equations are just like reverse of each other. And so therefore the Ka values and the Kb values are related to each other. And so it turns out that the third ionization of the acid is related to the first ionization of the base. And that's going to equal to Kw. And so whenever you guys are working with triprotic acid, wow, this is really messy. Whenever you guys are working with triprotic acids and triprotic bases, you have to make sure that the Ka values and the Kb values are correctly related to each other. And then we're going to go ahead and take a look at just one example looking at this in just a second. All right, so hopefully you guys understand the relationship between the Ka values and the Kb values for triprotic acids and bases. Hopefully you guys understand the relationship between the Ka values for diprotic acids and diprotic bases. So let's go ahead and take a look at an example, right? So now that we know how to write the chemical equations for each ionization step of a polyprotic acid or a polyprotic base, we're going to go ahead and apply this concept in a word problem type setting. So number one, it basically states that if you have 0.325 moles of ascorbic acid, and so ascorbic acid is vitamin C. And if it's found in 1 liter solution, we're going to determine the pH of the solution. So we're also going to determine the concentration of hydrogen ions at equilibrium. We're also going to determine the concentration of the conjugate of ascorbic acid at equilibrium. We're also going to determine the concentration of ascorbate, which is the full anionic form of the ascorbic acid at equilibrium. And then we're also going to determine the concentration of ascorbic acid at equilibrium. And so we'll be able to address all four of these as we try to solve for the pH of the solution. And the last piece of information that this problem gave us are the Ka values. And so whenever you guys are given 2 Ka values in your problem, that already implies that you guys are going to perform calculations related to polyprotic acids and polyprotic bases. Okay. And so before we start, we need to come up with like a solution map, right? And so whenever we want to determine the pH of the solution, remember that it's measuring the concentration of hydrogen ions at equilibrium. And so to determine the concentration of hydrogen ions at equilibrium, we need to determine the value for X, and that's coming from like the mass action expression. And so for us to write the mass action expression, we need 2 more items. we need an ice table, and we need a balanced chemical equation. Okay. And so we're going to go ahead and work backwards, I suppose, with respect to this solution map that I formulated. And so we're going to go ahead and write the chemical equation first, then the ice table, then the mass action expression. We're going to solve for x, and then determine the equilibrium concentration, and then we're going to determine the pH. Yep. And so here we're going to write the correct chemical equation. We are going to look at the chemical formula for ascorbic acid, and it's already given to us. And so notice that this is a diprotic acid. So let me just use orange in this case. And so since this is a diprotic acid, we're probably going to have to write the chemical equation to represent the first and second ionization of that hydrogen. Okay. And so the chemical equation for the first ionization is going to be H2C6H6O6. Okay. And that's, since this is the first ionization, it's representing Ka1. And so when you ionize this, you get HC6H6O6 with a negative charge and an H plus. And so remember, when we're separating a cation from an anion, the charge of the anion just dominates, so it's more negative. Okay. And so the second ionization step is going to be the conjugate of ascorbic acid, so HC6H6O6. And when that final hydrogen ionizes, you get well, let me be consistent. You get C6H6O6 2 negative plus another hydrogen ion. Okay. And so when you guys are trying to calculate the equilibrium concentration or the pH of the solution, you have to take into account both ionization steps. And so I'm going to go ahead and show you the long way of solving this problem, just so that you can understand the shortcut. And so when you guys are trying to determine the total concentration of hydrogen ions at equilibrium, you have to consider how many hydrogen ions are produced after the first ionization, and we also have to consider how many hydrogen ions that's produced in the second ionization. And once we add both of these up, then we can finally determine the concentration, the total concentration of hydrogen ion at equilibrium, and then we can determine the pH. And so to do that, we're going to go ahead and use the ice table. And so since we have two equations that we're going to be considering, we have to write the ice table for both ionization steps. Okay. And so I'm going to go ahead and copy and paste, just because I don't want to write this over again, the first ionization step. Actually, let me just copy this whole thing. Okay. And so for the first ionization step, we need to determine the equilibrium concentration of H+. And so to do that, we need to write our ice table. And so, if you look at the initial concentrations, here we have 0.325 moles for every 1 liter. And so if you divide those two values, 0.325 divided by 1 liter, that's going to give us a molarity of 0.325. And so we can go ahead and write 0.325 molar for the initial concentration of ascorbic acid. And so in the problem, it didn't really inform us any initial concentrations of the other substances. And so we're going to go ahead and put a blank for each of them. And so once again, since we're just transferring protons or ionizing protons, the relationship is 1 to 1 to 1 to 1. All right, so let's go ahead and look at the change. And so if you look at the value for Ka1, it's times 10 to the negative 5. So this is telling us that ascorbic acid is a weak acid. Also, it's not on the list of strong acids that I had you guys memorize. And so therefore, it's just going to be minus 1x. And basically, however much is consumed in the process when it reaches equilibrium, that's how much, that's how much is produced. Okay. And so at equilibrium, we just have 0.325 minus x, and plus x. And so now that we have our ice table, we can go ahead and write the mass action expression. And so Ka1 is equal to the concentration of HC6, H6O6 negative at equilibrium, raised to the first power because its coefficient is 1. And hydrogen ion is once again raised to the first power because its coefficient is 1. And this is going to be divided by ascorbic acid. So this is H2C6, H6O6 raised to the first power because its coefficient is 1. And then we're simply going to go ahead and plug in all of these values in our mass action expression. So in other words, we're going to take this x and plug it in here, take this x and plug it in here, and then 0.325 minus x is going to be plugged in the denominator. And Ka1 was already given to us as 6.70 times 10 to the negative 5. So we're going to go ahead and plug all of those values into our mass action expression, so that way we get 6.0 times 10 to the negative 5 is equal to x times x over 0.325 minus x. And so I'm going to go ahead and multiply these two x's so that I get an x squared. Once again, if you guys leave this alone, you don't make any assumptions, you're going to run into a quadratic equation. And so we want to determine whether or not we need this x in the denominator. Can we ignore this? And so once again, we're going to have to ask ourselves, is the initial concentration far, far greater than the Ka1 value times 100? And so if the initial concentration is 0.325, is this far, far greater than 6.0 times 10 to the negative 3? Okay. So basically I'm taking this Ka1 value and I'm multiplying it by 100. And this is the result that I get. And so the answer is yes. So this is a true statement. So therefore I can go ahead and ignore the x in my denominator. So that's going to be 6.70 times 10 to the negative 5, which is equal to x squared over 0.325. And so if I multiply 0.325 to the other side, I get x squared is equal to 2.18 times 10 to the negative 5. And finally, I'm going to go ahead and take the square root of both sides to cancel out the square. And the final value for x is going to be 4.67 times 10 to the negative 3. Okay. And so this x is once again representing the change, if you will, in the mass action, or I'm sorry, in the ice table. And so what we want to do is we want to kind of address some of these questions. So we want to determine the equilibrium concentration of the hydrogen, the conjugate base of ascorbic acid, the anion of ascorbic acid, and ascorbic acid itself. And so for this type of calculation, what I want to do is kind of tabulate the equilibrium concentrations that I have after the first ionization. So after the first ionization, okay, so we're looking at, I'm going to go ahead and copy this right here. So the equilibrium concentrations of H2C6H6O6 ascorbic acid is defined as 0.325 minus x. So this is 0.325 minus x. And so since this is x, it's going to be 0.325 minus 4.67 times 10 to the negative 3. And so that value is going to be 0.320 molar. Okay. And so this is the equilibrium concentration of ascorbic acid. Let me just move this over. And so, according to my ICE table, the conjugate base of ascorbic acid is defined as simply X. And so, therefore, the equilibrium concentration of the conjugate base after the first ionization is going to be 4.67 times 10 to the negative 3 molar. Okay. And last but not least, the equilibrium concentration of hydrogen ion is going to be the same value since it was defined as X in our ICE table. And so it's important for us to, or it's important for me to do this because what we're going to do later on is compare and contrast these values after we tabulate the equilibrium concentrations after the second ionization. Okay? And so I'm just going to go ahead and leave this here for now. And I'm going to go ahead and perform another set of ICE tables to determine the equilibrium concentrations of these components or these substances after the second ionization. Okay. And so I'm going to go ahead and write the second ionization, or I'm not going to write it, I'm just going to copy and paste. Okay, so we're going to go ahead and I'm going to go ahead and copy this and just place it underneath. Okay. All right. And so what we're going to do is we're going to figure out what the equilibrium concentration is for each of these components after the second ionization. And so to do that, I'm going to go ahead and write another ice table. Now, this is where things kind of get a little tricky, but it shouldn't be that tricky if you understand the concept overall. And so let's go ahead and look at the initial concentration. So the initial concentration, if you look at the problem, it only gave us the initial concentration of ascorbic acid, which is H2C6H6O6. And so here, when we're writing the second ionization, this is C6H6O6, and I think I forgot to write a negative charge there. And so since the problem didn't give us the second ionization, the initial concentration for the second ionization, it doesn't mean that we're going to blank this out. What we want to do is take a step back and think about the concept. So you have ascorbic acid, and you placed it in water. And so at some moment in time, the first equilibrium has been reached, and this value, 4.67 times 10 to the negative 3 molar, represents the equilibrium concentration of the conjugate base of ascorbic acid. And so when you start your second ionization, this value that you solved for is going to be the initial concentration for our second ionization. Bum, bum, bum. And so we're going to go ahead and write 4.67 times 10 to the negative 3 molar. Okay. And so for C6H6O6 negative 2, the conjugate base of this conjugate acid, notice that after the first equilibrium, after the first ionization, we didn't really produce this compound, and there was nothing in the problem that says that stated the initial concentration of this anion. So this is what we're going to blank out. Now for hydrogen ion, very similar to what we did with the conjugate base of ascorbic acid. This is how much that's already present in solution after the first ionization. And so there is going to be an initial concentration of hydrogen ion for the second ionization. That's going to be 4.67 times 10 to the negative 3 molar. Okay. And so these are the key differences between the first and the second ionization. In the first ionization, looking at our ice table, we only had an initial amount of this, and we had no initial amount of the conjugate base and the hydrogen ion. However, after the first ionization occurred, then we've created some amount of this and some amount of this. Therefore, when we start the second ionization, these amounts that we've calculated is going to represent the initial concentration of the conjugate base of ascorbic acid and that of the hydrogen ion. Awesome. And so if you guys are looking at the value of Ka2, I'm going to scroll up. So Ka2 is going to be 2.70 times 10 to the negative 12. And so anything times 10 to the negative 12, that's far, far less than 1. So we for sure know that this is going to be minus x, right? It's not going to be the initial concentration, that's the change. And so this is going to be plus 1x, and this is going to be plus 1x. And so when we add down, we get 4.67 times 10 to the negative 3. I'm going to put this in parentheses, minus x. That's going to define the equilibrium concentration of the conjugate base of ascorbic acid. And if I add down in my second column, I just get x. And if I add down in the third column where H plus is, this is going to be 4.67 times 10 to the negative 3. I'm going to put this in parentheses, plus 1x, or plus x. And so these expressions represent the equilibrium concentrations of each of these substances. And so we're now going to go ahead and write the mass action expression. And we are going to relate that mass action expression to Ka2. And so Ka2 is going to equal to the concentration of C6, H6, O6, negative 2, raised to the first, times this by the concentration of H plus, raised to the first, over the concentration of HC6, H6O6 with a negative charge, raised to the first. And so now that we have the mass action expression, we're going to replace every single one of these variables to either a value or an expression found at the last row of our ICE table. And so let's see here, Ka2 was 2.70 times 10 to the negative 12. That's going to equal to C6, H6O2, or O6, negative 2. So that's going to be x. And then all of this is going to be representing H plus. 4.67 times 10 to the negative 3 plus x over this item, this expression in the denominator. So it's going to be 4.67 minus negative, or times 10 to the negative 3 minus x. Okay, and it's all raised to the first power. Okay. All right, so this looks a little complicated. So what we want to do is we want to see if we can make some assumptions. So very similar to other problems, we're going to see if we can ignore the x in the denominator. And so if you guys are looking at the magnitude of Ka2 is times 10 to the negative 12, that's basically saying that there's really not much change that's going to occur if you compare it against 4.67. And so we're going to go ahead and ignore this bottom x. Now, what makes this ICE table a little bit different from the first is that we also are comparing the change to that of a tabulated value, much like what we did here in the denominator. So this is an actual value, and we're ignoring the change. And so if we ignore the change of the denominator, we can go ahead and ignore the change in the numerator, right? And so this is basically saying that the addition of this change will not significantly affect this value. And the value of this change is not going to significantly affect that value. The reason why is because the Ka value is times 10 to the negative 12. That's 11 zeros before you hit the first significant digit, which is 2. And so if we ignore both of these x's, then what we get is 2.70 times 10 to the negative 12, which is equal to x over, oops, let me write this a little bit lower. Times this by 4.67 times 10 to the negative 3 over 4.67 times 10 to the negative 3. And these two cancel. And so it turns out that the value of the change is equal to Ka2. And notice that if you take this value times 10 to the negative 12 and plug it into, this x and this x, you're still going to get the same answer. So it's still going to be 4.67 times 10 to the negative 3. And so that's not a lot of change that's occurring. So it turns out that since there's not a lot of change occurring, the initial values that we put into our ice table is going to be the equilibrium values after the second ionization of the acid occurs. So let's go ahead and summarize that statement. And so after the second ionization, we're going to go ahead and look at the equilibrium concentrations for this chemical formula or chemical equation. So I'm going to go ahead and just kind of copy this, and I'll erase some stuff. And so notice that the equilibrium concentration of the conjugate base of ascorbic acid after the second ionization is defined as 4.67 times 10 to the negative 3 minus x. And so this is going to be 4.67 times 10 to the negative 3 minus x. And so if x is this value, then we have 4.67 times 10 to the negative 3 minus 2.70 times 10 to the negative 12. And if you plug that into your calculator, what you get is 4.67 times 10 to the negative 3 molar. And so this is the equilibrium concentration of the conjugate base of ascorbic acid. And so if you look at the equilibrium if you look at the definition of the equilibrium concentration of ascorbate, it's simply just x. And so it's going to be 2.70 times 10 to the negative 12 molar. And if you guys look at the equilibrium, the mathematical expression that defines the equilibrium concentration of H+, it's going to be 4.67 times 10 to the negative 3 plus x. So 4.67 times 10 to the negative 3 plus x. And if you plug in the value of x, you get 4.67 times 10 to the negative 3 plus 2.70 times 10 to the negative 12. And so if you add both of these together, the equilibrium concentration of H plus is 4.67 times 10 to the negative 3 molar. All right. Yay, we did it. So we figured out the equilibrium concentrations after we performed the second ionization. And so What I want to do is I want to compare and contrast the values of the first and the second ionization and see if there's some type of pattern that just to see if we can just to see if there is some pattern. Okay. So I'm going to go ahead and erase some stuff here. Okay. All right. So I'm going to go ahead and highlight the values for the second ionization in yellow. And I'm going to go ahead and highlight the values for the first ionization in a different color. And so if you guys are looking at the conjugate base of ascorbic acid, after the second ionization is 4.67 times 10 to the negative 3 molar. Now, if you guys look at the first ionization, if you look at that value, here's that conjugate base. The value is the same. And so this is telling us that the overall concentration of the conjugate base is not going to change significantly after the second ionization. And the reason why it's not changing significantly is because if you look at the magnitude of Ka2, the magnitude of Ka2 is 2.70 times 10 to the negative 12. So we don't really care about this number, but let's look at this magnitude. Times 10 to the negative 12 is very, 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 very small. And so that is the relative strength, if you will, of this conjugate base acting as an acid. And so this is already telling you that there's not a lot, that the amount of this conjugate base is not going to ionize by a lot. Okay. And if you guys look at the concentration of H plus after the second ionization, and if you guys are comparing the concentration of H plus after the first ionization, once again, notice that they are the same value. And so the only thing that's a little bit different is the equilibrium concentration of this conjugate base, or I'm sorry, not this conjugate base, this anion, ascorbate. But if you look at the value, it's 2.70 times 10 to the negative 12. That's actually equal to Ka2. So let me erase this slash. That's equal to Ka2. Okay. And finally, if you guys are looking at the equilibrium concentration of ascorbic acid, we can determine that just from right after we performed the ice table for the first ionization step. And so this is telling us a couple things. One, we can go ahead and treat polyprotic acids like monoprotic acid. The reason why is because the second ionization or the third ionization step, that Ka or Kb value will be much, 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 much smaller than the first ionization step. So after the first ionization step, you can already determine the pH of the solution. The second or third ionization step of any polyprotic acid will not significantly change the concentration of hydrogen ion. And therefore, the pH is not going to be significantly different. If you were to, calculate it for the first ionization and compare that to the second. And so I'm just going to go ahead and put a little note here. Okay. So we're going to treat polyprotic acids and bases like monoprotic acid or a monoprotic base. In other words, we can determine the pH from the first ionization. Okay. We don't have to do another ice table just because the second Ka value, Ka2 or Ka3, will be significantly less than the first ionization constant. And so if I scroll all the way up at the very beginning of this problem, here we have 6.70 times 10 to the negative 5. And if you look at the second ionization, its relative strength is 7 orders of magnitude less than the first. And so this is telling you that it's a very small population, an infinitesimal small amount of that population of the conjugate base will actually ionize one more time to produce another H+. Okay. And so for your problems, you can go ahead and calculate the pH for a polyprotic acid or polyprotic base after the first ionization, just because the concentrations does not change between the first and the second ionization. And we can go ahead and conclude that the anion the concentration of the anion is equal to Ka2 or Ka3 if you have a triprotic acid. And so what I mean by that, that's going to represent, let me see here. So the anion is an orange, so I marked that in orange to represent this guy. So if I ask you to calculate the equilibrium concentration of the full anion of the acid, then that's already going to equal to its Ka value. So you guys don't really need to perform a second ice table. You guys can if you want. If you understand this math, then you guys can. I'm not stopping you. However, if you want to kind of expedite your work, you can go ahead and make these relationships. You can make these conclusions. And so I'm showing you why I can make these conclusions just by comparing these values. So hopefully when you guys are performing these types of problems on your own, you guys can go ahead and just choose just one path. You guys can do 2 ice tables and you'll still get the same answer, or you can go ahead and follow these assumptions to determine, for example, the pH of the solution and the concentration of the anion. Okay. So before I stop this video, let's go ahead and determine the actual pH of the solution. And so after the second ionization, notice that we have 4.67 times 10 to the negative 3 molar of H+. And so we're simply going to plug that into our calculator. So we're going to take the negative log of 4.67 times 10 to the negative 3. And then that's going to give us our pH. And so I'm just going to go ahead and type that in really quickly. And since I have 3 sig figs, I need to report 3 decimal places. And so my pH is going to be 2.331. Okay. All right. And so once again, I can't emphasize enough that the concentration of the hydrogen ion after the first ionization is equal to the concentration of hydrogen ion after the second ionization. And so if you guys just wanted to do one ice table, and then from this value, you guys can calculate the pH. Okay. All right. So that's pretty much it for this first video. I'm going to go ahead and stop this video, and we're going to look at one more example. And the next example is going to highlight the base, right? So how do we solve these problems for a polyprotic base? All right, guys, see you in a few.